So a lot of the work that I'll talk about today will be, it's partly in collaboration with some of the folks I list here, Sean Couch at MSU, Mike Pecos, Caltech in this fall, Josh Dolans, Jared Goldberg, Bill Edelman, and Frank Toomey's, all of whom I've worked very closely with on different projects, either in the past or that I have plans to continue to work on in the future. But I hope by the end of this talk, I can help motivate some of the things that we're trying to address in the remarkable deaths of these massive stars. One of the things I like to do is sort of start off with an overview and kind of tell you what I will tell you, if you will. I'm going to start with an introduction. I'm going a little bit into the core collapse theory, try to paint a picture of how we expect most massive stars might end their lives, discuss a little bit about the explosion mechanism, which will lead us into talking a bit about some of the problems that we have in the field in core collapse theory that has been presenting some challenges in changing how we approach the problem. That'll lead into what I've been focusing on in my work recently, in my research, where I've been modeling the three-dimensional collapse of these massive stars in the final moments before the actual iron core collapse. And so capturing what that 3D structure looks like prior to explosion as a potential solution to some of these problems we're facing. I'll present some results investigating a range of different 3D progenitors, also focus on one of the recent results that I recently published on a rapidly rotating 16 solar mass star. And then I'll wrap up briefly on some signals that core collapse supernovae can produce and how these new sort of 3D progenitor models might affect those signals. So starting off, the death of a massive star, why should many folks care? I imagine a lot of folks in the room do care in some areas in terms of the massive stars, because they play a big role in a lot of different parts of astronomy. Some of the things that I like to think about is the stellar transits they produce, right? And so you can have a massive star produce core collapse supernovae, collapsar, gamma ray bursts, superluminous supernovae, many different stellar transients that a lot of folks are working on characterizing when they are observed. They also produce compact objects, and so they'll produce the neutron stars that are being detected by LIGO. They'll potentially produce stellar mass black holes that eventually go into systems that are potentially detectable by things like LIGO and other such systems as well. They're very important for galactic chemical evolution, and so whether it's during the evolution of the massive star's life, during the explosion, or even during the neutron star merger, there are many ways in which massive stars play a role in producing different types of elements that are important, as well as the feedback that they have in their surrounding mediums. And so one of the things that I've been really focusing on and thinking about lately is the multi-messenger signals that they produce, and sort of tying that in together with the different aspects that these new progenitor models that we're building, how they might alter how we interpret these multi-messenger signals. So speaking very briefly about some of the general characteristics that we have for core collapse supernovae, we expect about 3 per century for a Milky Way type galaxy. They liberate a ton of neutrinos, and they have kinetic energies on the order of 10 to the 51 erg. And so keep that number in mind. I'll talk a little bit about some of the challenges when we're modeling these solar explosions and getting something that agrees with what we observe. And so they're thought to be sort of the end fate, the end product of a massive star with about 8 times more mass than the sun, so massive stars. So taking us through the final moments of a massive star's life, what does that look like? And so here I have a diagram that's definitely not to scale, but shows sort of this onion shell-like, or I gave a public talk last week and someone suggested parfaits, like from Shrek, because I argued that stars are not very onion-like. But this diagram shows the different burning processes that have taken place in the star's life, where you have iron in the center, this iron core that's produced, and the remnants, the ash built on top of that. In this simplistic picture with different timescales shown for the different burning epochs. But the idea is that you form this inert iron core. Core becomes unstable, and then eventually it collapses rapidly. So this is the beginning of the end, if you will, for a massive star's life. And so digging deeper into the physics of that iron core that is collapsing, so this iron core might have these physical properties. Some density is about 10 to the 10 grams per centimeter cube, radius of about 2,000 kilometers, and then it will collapse on the order of a couple hundred milliseconds. Oops, skip the slide, I think. Yeah, and so it eventually, it will reach a bounce phase where it produces this protoneutron star, has some radius, has some density, again, a much higher density. But what happens is during that bounce, a shock is formed, and that shock can, well, in early theories, it was believed that can move out and promptly explode the star. But it turns out that that shock loses energy as it moves out, and you reach this what's called the stalled shock phase on the order of about 100 milliseconds. And so you go from something from the core collapsing, creating this bounce launching a shock, and that shock eventually stalling. But we know stars explode. And so one of the things you want to ask yourself is, how do you revive this stalled shock? And so we actually have simulations that shows this sort of stagnant stalled shock phase. Where on the right here, I have a diagram showing entropy of a 3D explosion model of a 20 solar mass star. This is work by Evan O'Connor and Sean Couch of this phase, where we have the protoneutron star in the center. We have a shock that has reached some radius, but is now in some balance where mass is falling inward and material is being heated from the interior. And you're trying to drive that shock outward and successfully bind the stellar envelope. And so one of the main mechanisms that we like to think about when we're modeling these stellar explosions is the delayed neutrino heating mechanism, which taps into some of that energy from the protoneutron star to help heat that stalled shock and eventually drive successful explosion. And so it capitalizes on some of the energy that's released as that neutron star contracts post bounce. So after it has actually bounced, that heating can eventually drive the stalled shock to explode a star. So we actually, you know, this is one of the main mechanisms that we believe for ordinary type massive stars that might end their lives in this way. So this sort of has been the picture for 3D explosion models, where here I show some of my favorite volume renderings. Where here we're actually looking at entropy, which is a really good field to render for volume rendering, because you can visualize a protoneutron star, which you might see in the center in some of these visualizations, and then the convection or the movement of the material above that protoneutron star as it's being heated, as well as the edge of the shock as it's moved outward, as it's moving outward in some of these very asymmetric explosions. So to paint a picture of some of the challenges that we face when modeling these explosions, you have to take into account rotation and magnetism. And so magnetohydrodynamics, that top left here, that green box. General relativity is also important. You know, you're dealing with very dense material, and that can be something that can lead to qualitatively different results. How you treat the transported neutrinos, so your main heating source, that's very important as well. There's different ways to approximate that. Then the microphysics, very down, you know, used in your simulation, those can also have impacts on your results as well. And so coupling all these things together, determining which has the lowest impact and how you might approximate these different methods has been a big challenge in the field. In addition to that, there's also open challenges, despite all of these sort of approximations or approaches that people have taken. So one of the things that folks have done is they take one-dimensional stellar evolution models, so from codes like MESA, Kepler, and then they'll map them into their three-dimensional 2D multiphysics hydrodynamics code. And here on the right, I have a visualization of the explosion I showed from earlier, that still image, of doing just this. So you take a 1D model, you map it in, you explode it, you follow the evolution post-bounce, and where we're visualizing entropy here, we have that protoneutron star in the center. We have a shock that eventually starts to sort of oscillate about the protoneutron star, something called the standing accretion shock instability. But the challenge is, which what they found in this model, is that this model fails to be revived. So that shock, that stalled shock, is actually not revived because heating is not efficient enough to actually drive successful explosion. And this presents a challenge with when we believe that these models should explode, but then we're using our sort of multi-physics, sophisticated state-of-the-art hydro code to explode these models, and that shock's failing to be revived. So some of the sort of listing some of the challenges that have been faced in the field, an additional challenge that we often think about is explosion energy. And so on the right here, I have a diagram showing the post-bounce time on the x-axis, which is a measure of the start of the explosion, and the y-axis is the explosion energy in units of beta, so 10 to the 51 ergs, where for most of these simulations, where each different color line is a different initial 1D model from a different initial stellar mass. We're finding that it's hard to match these energies to what the observed range is, what the estimates are from the literature of about 0.5 to 4 beta, all the way up to the most energetic explosions. And so this is, contention between the 3D multi-physics explosion models and what we're observing, what we expect to observe in the literature. And so you might argue that some of these have not reached their sort of asymptotic limit. So there's also a need to be able to evolve these out farther. And that's something I'm really excited that we're working on. At LANL is sort of these next generation codes that allow us to run these stellar explosions more efficiently to be able to evolve to later times. And so again, reiterating, so that shock revival problem that we saw from the previous slide, models fail to explode. So even if they do explode, the energy is low, or they might just happen to fail to explode when we expect them to otherwise. There's also a big challenge with the fate of the compact remnants, right? Following that protoneutron star out post-explosion, and also understanding how it might interact with another binary companion if that exists in the system that you're exploring. These require long-term simulations that are very computationally challenging and present really open, active areas of research in the field that's motivating a lot of the work that we do. And so some of the solutions that folks have looked at, one of the ones that I like to list is GR, so including general relativity in your model. So not assuming that you have a Newtonian fluid, but you actually have something that solves, or to some approximation, the general relativistic hydrodynamics equations. Folks have found that can lead to more compact protoneutron stars, which can lead to larger neutrino luminosities, which is what was found in this volume rendering on the right from an explosion model from Luke Roberts' work in 2016. So that's one potential solution. Neutrino transport, right? That's also something that folks have been really pushing on, is alleviating this sort of, I guess, spherically symmetric, sort of this light bulb heating model, if you will, because it's computationally cheap. In some cases, it's easier to implement. That could be one potential solution, as well as moving beyond that, getting something that has angle dependence, velocity dependence, includes many different interaction types. That could be one potential path forward. One of the things that I've been concerned with lately is looking at the initial models, the perturbations. And so I like to argue that stars are not onion-like, maybe parfait-like, but they're definitely not spherical, and they can vary a lot. And so that's something I've been pushing on a lot in my research lately. So when we take a deeper look into these pre-supernova models, there's been work that's been out. Here I'm showing a visualization of a 3D, a 15 solar mass star involved in three dimensions, but it's an octet simulation, but this is capturing the collapse of a 3D, of a 15 solar mass star. And so we're visualizing the magnitude of the velocity field here, where we're advancing in time from left to right. But what you see is the iron core in the center. You have the silicon shell above that, and then above that is the oxygen shell, which is non-convective in this model. What they find is that when you evolve this, you can have velocities on the order of about 500 kilometers per second near collapse in 3D, something that is not captured easily in the 1D simulations. And so they evolved this for 3 minutes using a approximate network. And then when they map this into their code, you can then collapse that model all the way down to bounce and follow through the explosion, where here we have, again, on the x-axis, the post-bounce time, y-axis is that angle average shock radius. When you take that 3D initial model and you take an angle average of that 3D initial model, so you essentially wash away all the non-radial perturbations, you get something that's completely different between these two explosion models, where sort of the cyan or the higher up line is that 3D initial model. It explodes more promptly, more energetically, and then the 3D angle average model, it also explodes, but it takes a bit longer. You can imagine a scenario where a model is very close to being, or it's failed to explode, but when you have these 3D initial conditions, actually explodes. So now you're changing qualitatively what your 3D multiphysics code is saying is the outcome of this stellar explosion. Folks have also looked at alleviating this approximation of assuming octant symmetry, and they've evolved in 3D these oxygen shell burning simulations, and then they've used those as input as well. And so here I'm showing a slide from Bernard Muller's group where they took that initial conditions and they ran it through and they exploded it in their code, and they compared it again to this angle average model, where here we're visualizing entropy slices of their 3D explosion models. So on the right, it's the 3D initial conditions, showing very asymmetric shock morphology, where the shock is actually moving out to larger radii. You'll notice the scales are different between the two, where on the left, you have successful explosion. On the right, you start from that 1D spherically symmetric. You have something that looks similar to what we saw in the movie from earlier, where you have this sloshing about the protoneutron star as that shock is trying to be successfully revived, because the heating is not as efficient as is in the left. So you might ask the question, how do these 3D progenitors help facilitate explosion? And so some of the things that we like to list or sort of point out as we're thinking about and motivating these pre-supernova models is seeing if we can observe large Mach numbers in these convective burning shells. So folks have found that these can lead to density fluctuations during collapse that actually lead to favorable explosion conditions for the explosion models. There's also this observation that folks found, especially in that Muller paper from the previous slide, where there's an increase of mass in the gain region due to this non-radial flow. So by capturing the non-radial components of the velocity field in the post-shock region, you can actually have more matter be moved into the gain region that is actually helping facilitate where here this inequality is on the left is the effective neutrino heating rate proportional to the mass in the gain region. More mass in the gain region, more efficient heating to help drive that shock. Folks also found work by Sean Couch in 2014 and 15. They found that this increase in non-radial kinetic energy, which is also something you have with this non-radial flow, you observe it to be at large scales, which is also something that helps drive explosion. It's favorable for explodability when you have kinetic energy at large scales. A lot of folks have been observing that in their models. So this all really motivated what I've been focusing on lately is how we build better pictures of these pre-supernova models and assess their potential for solving at least part of the problem that we're facing in core collapse theory. So going into a little bit of our approach for modeling 3D stellar convection, you can start from simplified initial conditions like this on the left, where you have a 1D MESA model. You take that from some time right before core collapse. This is for a 15 solar mass star. And then you map that in, you take the density, you take the electron fraction, excuse me, and then you can actually, we're here on the top, you can see the iron core is sort of denoted by these arrows. Above that are the different silicon, oxygen, neon shell regions to give kind of an idea of the interior components of the star that we're capturing. The dashed line is the edge of our domain. So you can start with something like this, and you can end up with something like this on the right, where we map this into Flash, we evolve it in 3D, and we're visualizing here the velocity field in the oxygen shell burning region and the moments near collapse. And so in the center, you see that iron core that eventually falls inward as it grows in mass and then eventually becomes dynamically unstable and collapses. And then we can also see a wide range of convective scales occurring in this oxygen shell region, something that might differ from what is captured in 1D in codes like MESA or Kepler. And so this is a work I found in 2020, focusing specifically on these oxygen shell regions, as this is one of the most important regions, at least this innermost region, in terms of what will be accreted onto that neutron star, what will reach that gain or that shock surface in the during the stellar explosion. And so this was about 7 minutes before collapse that we evolved this 3D model. And so we wanted to build on that. So in that paper, we looked at 2D, 3D. We also explored some octant symmetry models, and we're able to quantify those results. What I wanted to do is sort of build on that a little bit more and survey different initial progenitors. And so what I did was I evolved different initial 1D models. So we looked at 14, 20, 25 solar mass initial conditions from MESA again, to survey a wide range of initial configurations. So on the right, we have a diagram. On the x-axis is the mass coordinate. So spatial coordinate, where a lower value means you're more towards the center of the star. A higher value means you have enclosed more mass, and so you're further out in terms of the radius. On the top panel, we have the convective velocity. Middle panel, oxygen mass fraction. The bottom panel is the silicon-28 mass fraction. And so the main thing, this is a pretty complex plot. One of the main things I like to take away from this is that for the different colors, they all sort of vary for these different quantities. And so we wanted something where, say, there's a thin oxygen shell or extended oxygen shell in a different model. This is the population you might realize when you run these 1D models, and you're seeing these different structures form in the moments near collapse. And so we took these as our input to see how much this variation in these different properties might lead to different things that we observe when these are modeled in 3D. And so we did that. We started with these models, and we evolved for even longer, 10 minutes before collapse, to hopefully capture more turnover times within these convective turnover times in these different regions. So on the right, here I'm showing the bulk properties of these different 3D stellar convection models. Where from left to right, we have silicon-28 mass fraction, we have the radial velocity, and we have the radial Mach number. So if we start from the top and go down, you have the 14 solar mass, the 20 and the 25 solar mass model, where qualitatively, they're all kind of different. So the 14 one is pretty weak convection, if you will. It actually takes a while to get spun up. The 20 solar mass model is very chaotic. It has very large scale flow happening. That's that center panel. And then on the bottom, you have something that's maybe in between. You have a model that's slightly different. And so we're seeing convective speeds that range based off these different initial conditions, which maybe you might expect that. We're observing large scale flow observed in 20 solar mass models. One of the things, recall that these large scale flows in these burning shells are something that are favorable for collapse, as well as these Mach numbers. And so what we're finding is that there's not one very simple answer for each initial progenitor that you might produce. And so as we're building more models, we're able to capture what is more likely a population of what massive stars look like near collapse, and get a better understanding of what the ranges are for the Mach number, convective speeds, and other such properties. Yeah, so here we have that sort of looking at the Mach number again. So when you're thinking about these models as input for your explosion models, we want a good idea of what the parameter space is. You can also do things like use these 3D simulations to inform. Yep.
Carl, we have a question.
Okay. Just a quick question. When you map from MESA, where the profile is calculated assuming convection and a mixing length approximation, to your 3D equilibrium where everything is determined self-consistently, in principle, there must be some transient flow associated with that transition. And I mean, are you relaxing to a steady state in the convection where you can say the transient is definitely being lost?
So I'm going to repeat your question, make sure it is correct, or I heard it correctly. Are you asking if we evolve these to reach a steady state to make sure that we weren't just capturing the transient from mapping to Mesa to Flash?
Yeah.
Yeah, so that's a good question. Yeah, that's one of the reasons why we wanted to extend how long we were evolving these models, because there will be a transient. We worked a lot on minimizing that transient. That's why I'm really excited with this new hydro solver that we use, because it's really good at keeping that iron core more stable, reducing that initial transient. But yeah, so we have to account for that. It can last upward to 100, maybe 150 seconds sometimes as it traverses the domain. There's also potentially some reflection that takes place. But then after that, depending on the configuration of the shell model, we're able to capture more or less a few turnover times within these shells to reach something that is a quasi-steady state right before it eventually becomes nonlinear, and then the contraction of the iron core sort of accelerates things. So that's something that we've definitely kept in mind, and I would argue that we've captured enough turnover times in all of our models to say we've moved far enough from that initial transient. So one of the things I'd like to do with these simulations, and that we've shown in the paper, is comparing them to different mixing approximations, or at least just comparing them to the Mesa models. And so here on the right, we have a diagram showing the mass coordinate on the bottom axis. On the top, we have the convective velocity speeds. We're taking what's spit out by Mesa, it's that dashed line. And then here at the solid line for our 3D model, this is for a 20 solar mass, we're taking the non-radial component of the velocity field. And so you could define the convective velocity in a lot of ways. This is how we defined it for this paper. And this is a non-rotating model. And then we're observing these differences where the extent of the oxygen shell is slightly different. The speeds are different by a factor of a few. And you're noticing differences between that lead to different things like what we see at the bottom, where at the boundaries, there's sort of the smoothing out of these compositional gradients as you're looking at these different mass fractions, where the solid line, again, is the 3D model, and the dashed line is the 1D Mesa model. And so when you have these 3D data and you're able to observe these things, you can start to think about how you fold that back in, what might be taking place that's more efficient in 3D, to sort of get an estimate of where that variation is as compared to Mesa. And so looking more specifically at one of these models in terms of the mixing, we took our 20 solar mass model, and here we're plotting slices of the carbon-12 mass fraction. Where here, the top panel, we have the 20 solar mass model that I showed from the previous slide. And we're showing the carbon-12 because we noticed this sort of layer of carbon above our oxygen shell, which is the main thing that we looked at. And then we can see mixing taking place as carbon is sort of moved down into the oxygen shell region. And if you look at between these models, as you move left to right in terms of time, you advance in time, where the last slide is right before core collapse. There's differences between the top panel and the bottom panel, where the bottom panel is actually us initializing our convective velocity field slightly different. And so what we found is that when you initialize it using a different spherical harmonic degree, you could get this increase in carbon being pulled down or entrained into the oxygen shell region. And the reason this is important is because things like mass entrainments, particularly for carbon-12, can very much affect galactic chemical evolution models and potentially produce more, in this case, odd Z elements, which are actually underproduced in galactical chemical evolution models. And so folks have done papers on this where they have shown for extreme sort of entrainment rates, you can actually get something that matches observationally. So we're seeing something that's pretty in line with what other groups have seen here, where I argue there's a little bit more entrainment at the top panel. We show these details in the paper. But one thing I was excited that we were able to point out is that I guess your initial conditions for your initial conditions is important. So having an idea of how these affect your models and the properties that you pull out of them is something that is important and something I'm glad that we're looking more closely as we evolve more of these models. So if you're like me and that slice isn't exactly the most illuminating, you might be more, well, I think there's supposed to be a movie playing, but I guess you have a slideshow now. So yeah, so this is that same slice plot that I just showed, but in a movie format where we have the iron core in the center. We have the silicon-28 mass fraction that's being visualized, and we're seeing this mixing in 3D here, where carbon is sitting sort of at the top of this region that's being visualized, and the more gold or yellow regions are that carbon-12 being mixed in. So this is a volume rendering of that. So you can do things like this. You can measure sort of mixing entrainment that you observe in your 3D simulations. You can work to compare that to MESA, see how that might impact galactic chemical evolution models. But these are all things that are falling out of our 3D pre-supernova models that are sort of outside of what we originally set out to explore with these simulations. They're allowing us to connect in many ways outside of what we initially set out to do. So one of the things that I was excited that we were able to do recently was this model I have on the right, where we're showing, here we're looking at the neon 20 mass fraction. So basically a field that will track sort of the convective, the qualitative convective flow patterns for a 3D rapidly rotating model, 16 solar mass model. One of the things that we found was that this model, the angular momentum is redistributed in a way that is different from what MESA predicts. And so we found that the turbulence was very efficient in mixing up the angular momentum within this oxygen shell as you evolve this model to collapse. And so we took this model again 10 minutes prior to collapse, we evolved this in 3D, and then we were able to capture this angular momentum redistribution. One of the things that I was excited that we were able to do with this model is that we can actually then take these angular momentum profiles, and then you can compute things like the protoneutron star spin, and you can find estimates of on the order of 1 to 5% differences between these different angular momentum profiles that were enabled by our 3D simulation. And so one of the things that was particular about this model is that the silicon and oxygen shell were pretty separated, if you will. But you can imagine a scenario where you have very tightly coupled silicon and oxygen shells sitting right next to each other that are undergoing convection, and the convection is quite turbulent, where that angular momentum is really redistributed and tends towards something that is not accounted for in 1D. Then you have a larger difference in the protoneutron star spin estimate once you integrate that angular momentum profile inward. So showing that plot from the paper where we looked at this in more detail, we have on the x-axis we have mass coordinate, y-axis we have the y component of the specific angular momentum, because this rotated about the y-axis. But what I'll point out is that so we're comparing this to the MESA model at collapse versus an angle average of our 3D model at collapse. And so we have two regions here. We have the oxygen shell, which we just showed in this volume rendering. So focusing on that first, we have for the solid line something that tends toward a constant, quasi-constant maybe, angular momentum profile in this turbulent convective oxygen shell region. Whereas MESA predicts something from this dashed line, which is more like a slope. And so you can imagine a scenario where you have an oxygen shell like this, very tightly coupled to the silicon shell, which is at a closer in mass coordinate, that redistributes the angular momentum in a way that's different. Rotation is very important in playing a role in this. And so, as with this first model that we evolved, one of the things that we're excited to do is look at a general population of not so rapidly rotating models, but models that rotate closer to what we observe, in agreement with what we observe, and start to build a population for what these angular momentum profiles look like in these 3D models as we're evolving them, and getting something that we can hopefully fold back to MESA and work to build a more accurate model of the late stage burning phases deep inside that stellar interior, as it plays a big role later on in the collapse of the star. And so now I want to talk a bit about how we've been building new stellar models, models of stellar explosions, where, before you might start from something like on the left here, these initial conditions that we started with from for a progenitor model or pre-supernova model. And instead you can start with something like this, where you have this, this complex 3D structure. You collapse that down, you port that to the explosion component of your code, and then you follow that explosion in 3D, where hopefully this visualization, these are not to scale, by the way, these are both different scales, but on the right we have an explosion model, a 3D explosion model starting from 3D initial conditions, where we have the protoneutron star in the center, we have convection taking place above that, and that shock radius eventually is starting to be heated up and eventually starts to move to a larger average radius in this simulation. And so we were able to follow that pre-supernova, the final 7 minutes before collapse, all the way up to, I think this 3D explosion model on the right goes out to about 0.5 seconds post bounce. So when you look at some of the properties that we're concerned with, like the shock radius, what is the difference between these different models? You have something on the right where we have post bounce time, x-axis, y-axis is the shock radius. Each different color line shows a comparison between a full 1D or a full 2D or 3D initial condition and the counterpart where you have an angle average of that. So guiding your eyes on this diagram, these are the two 1D models, where one is from MESA for the 1D initial conditions. The other one is an angle average of our 3D model. And so even for these two models, they're both exploded in 1D. You're noticing a slight difference in the explosion time, where the explosion time might be where the shock reaches, I guess, 200 kilometers in this context. And then these other two models are the 2D explosions, where we have one starting from a 1D model, one starting from a 2D initial condition. They're pretty similar, but there's a slight difference with the actual 2D initial conditions, where it reaches a larger radii earlier. So that's something I'll show, sort of the impact that has on the gravitational wave signal, but we're noticing differences there. Our 3D model is shown at the bottom, which is looking like it's about to turn over and explode and reach something that is in line with maybe the 1D models at a later explosion. But this is the type of thing where you can start to determine how these different initial conditions lead to potentially qualitative different explosion outcomes. And so folks have looked at or considered what would be the impact of these 3D progenitors, or at least these convective perturbations, on gravitational wave emission. And so on the right here, on the left, excuse me, I have a gravitational wave diagram showing on the post bounce time and the frequency and the amplitude of the gravitational wave signal. For a 3D explosion model, this is from Evan O'Connor and Sean Couch's work, where this model has no perturbations. So they did not perturb it, they just took that 1D initial condition and then exploded it. And then on the right here, we actually have that same explosion model, but starting from a perturbed set of initial conditions, where they actually alter the velocity field to mimic what we have in our 3D initial condition models. So they perturb where the silicon shell is, and they perturb where the oxygen shell is. And what they find is that once these silicon shell is accreted onto that protoneutron star during the explosion, you have an amplification, you have an increase of the gravitational wave strain that corresponds to that time over these broad range of frequencies. And so they observed that you can have, these perturbations will show up in the gravitational wave emission. And so having a solid description and accurate description of the pre-supernova characteristics before collapse is now translating to what we expect to see in our estimates for things like the gravitational wave emission. We found this in the work that we're working on right now with these 2D explosion models, where we have the angle average one, this purple line, and then the cyan or turquoise line, where we see this increase in the gravitational wave amplitude once that silicon shell is accreted around about 140 milliseconds post bounce here. On the y-axis, this is the plus polarization of the gravitational wave strain times a very optimistic distance. So this is what we're finding in our explosion models as well. So you might ask, will current detectors be able to detect these at some, I guess, optimistic distance? So I like to always place, if I show signals or estimates, I like to place them in the context of what we can do. So this is a diagram I like from Kuchen Pan's work in 2021, where Kuchen actually was able to show the gravitational wave signals and where they lie within the Bands LIGO and Kagra bands for 3D explosion models, where each different color line shows a different rotational speed, with the purple line being non-rotating. But actually, once you get something that's rapidly rotating, you have an amplification of the signal, and you have something that actually is closer, is more in the wave, the detectability range for this characteristic strain, as we're showing here for these different frequencies. And so one of the things that also folks have been able to do, and there's been a paper that's come out recently on this, is that you can actually move the detection distance out some distance using low energy neutrinos. And so there's been a lot of work that folks have been doing with combining gravitational wave signals, estimates from low energy neutrinos. So this is something we're also excited to do, is see what this impact might be on the neutrino emission from these new progenitor models, because that's something that might help us detect something that's a bit further out. So yeah, this is really exciting work. I always like to place in the context what our models might mean observationally. And this is something I think is really important too, if we're trying to build sort of state-of-the-art gravitational wave templates, something that has the bounce signal, something that has convective perturbations included, something that takes into account if SASE occurs, and how all of these might alter the signal that we estimate from explosions of these massive stars. So that brings me to my last slide. I want to go over some of the key takeaways that I have for this. So I argue that 3D models of stellar convection are necessary for an accurate depiction of stellar models near collapse. We saw convection occurring on many scales, with large dominant modes in some cases near collapse, the likes of which are favorable conditions for explodability. We found 3D instabilities that can affect flow properties such as mass entrainment, where in some cases we have more carbon-12 being mixed down, something that has implications for the nucleosynthesis of the subsequent nucleosynthesis of that model. We saw Mach number profiles, or at least slices that show favorable conditions for explodability again. In some cases, not all of them, you can have Mach numbers reach an appreciable fraction and eventually lead to these good conditions for explosion, potentially solving that problem that we initially set out to hopefully address. We looked at a rotating progenitor model and how the angular momentum was actually redistributed in a way that diverged from MESA. It'd be really exciting to explore that for different rotational speeds, rotational profiles, and see if this is something that is potentially can be folded back into, I guess, new models for MESA that allow us to tie into what these 3D data are telling us about how angular momentum is transported near collapse. We also looked at the multi-D explosions of the multi-D progenitor models and how those can help sort of alleviate some of these challenges, but how they also led to differences in the signals that we produce, and how that needs to start sort of be taken into account, because they can affect what our sort of predictive capability is if we're trying to make gravitational wave templates, estimates for the neutrino emission, and so on. And so one last slide I want to talk about, so just briefly go over some of the things I'm excited about. So looking forward, there's this code we're spinning up here at LANO called Phoebus. 51 Hertz blows up a star. It's being led by Josh Dolan's, Jonah Miller, Ben Ryan, and Luke Roberts. So it's this GR-MHD code, full neutrino transport. It's a variation of the variable Eddington tensor method for neutrino transport. No idea what that means. I'm still reading about it, but it's a GR-MHD code It currently supports fixed spacetimes, dynamical spacetimes in the future. We're really excited about this because this is really setting the framework for being able to do these simulations very efficiently and addressing a lot of the challenges that I've presented in this work. This is going to be an ideal tool for binary neutron star mergers, following the remnants evolution post merger, and also the actual explosion. And so connecting these using this next generation code is something I'm excited about. Flash X is also something that I'm really excited about. It's being developed. I think that's going to be really good for supporting very large scale or larger nuclear reaction networks instead of just following 21 isotopes. As we start to move beyond some of the models that I've presented and start to address things using the next generation of these computational tools. And so I wanted to bring this slide in and talk a little bit about these things I'm excited about, where we're looking in the future, to hopefully spark up some conversation during the question session, or if folks want to chat offline, I'd be happy to chat. But with that, I will end and answer any questions. Thank you.
Much, Carl. Question for Carl, and if you can use your table mic when you're asking your question.
Hi, Carl. David Spergel. Thanks for a really nice talk. I wanted you to kind of project forward to the post-explosion and these inhomogeneities that you're generating in the pre-supernova phase. How do you think this will affect, well, the nuclear synthesis and the distribution of inhomogeneities in the supernova remnant and its heating and so on?
Yeah, that's a really good question. That's something I'm really excited about with Phoebus, because we can evolve these explosions very late in time. So you can then start to think about, okay, how do we go from 3D collapse initial conditions to something that builds this very asymmetric and homogeneous distribution of different elements, and matching that to observation. So Phoebus is going to allow us to evolve that shock much further out than previously before. And that's something I'm really excited about. And so I think that's a big goal of mine over the next year or so, as we get these models spun up, is following that shock out as far as we can, and really working hard to connect to observations to connect to supernova remnants, because those are what we're hoping to realize and what will probably come out of these models.
I have a question for you, Carl. So you know that in this business of pre-supernova study of massive stars, there's been a lot of interest coming into understanding the effect of internal gravity waves excited by some of this convective or shell convection regions. And some of this must be in your simulation. I'm wondering how much you guys have spent time in trying to do understanding the excitation process and maybe even propagation of some of these waves.
Yeah, that's a great question. I'm actually collaborating pretty closely with Philip Edelman here at LANL. And I've actually produced used some of his scripts to characterize some of the velocity field, the rate of velocity field, and look at if we're seeing some of these modes. I'll tell you some of the preliminary results. I don't have any slides on them, but we're not observing any standing modes with like some of the things that folks Philip has seen in some of his previous efforts in modeling this. And I think part of that is that as we evolve this model in time, the width of these different shell regions alters as you move towards collapse. And so either the silicon shell gets larger, the oxygen shell gets more compact, or some combination, which I think is potentially making it hard for these standing modes to show up. But I do think we're observing excitation of other modes. And we're actually working on, as we have a meeting next week planned, to see if we can start to characterize what that looks like. And so that's another thing that we're really excited to hopefully have come out of these models, because like you say, they're probably very, they're probably in all of the simulations I've presented so far. We've only really scratched the surface of what we've analyzed so far.
Chris.
Thanks also for the great talk.
Quick question, maybe a bit broader. What's the present understanding of how the asymmetry of the explosion and say the magnitude of the kick the neutron star would get is correlated with other properties of the core before the collapse? Or are there any trends that are emerging?
So I'm going to say the question back. So are you asking if these asymmetries in the pre-collapse lead to, I guess, differences in the protoneutron star kick?
Well, that's, yeah. Good way of phrasing it, yeah.
Okay, yeah, no, sorry, it's a little hard to hear. Yeah, I think that's something that we're really excited to investigate a bit further. I think that's going to be a big piece of what comes out of being able to evolve these explosions using 3D initial conditions to late times. We're going to be able to get these estimates and start to build up a model of what the distribution for that kick is based off, as compared to a spherically symmetric initial conditions. And so a handful of folks have done this. I think there's one model from the last 7 minutes to the first 7 seconds, a paper by Bernard Muller's group, where they took this 3D explosion and evolved it 7 seconds out. They made some estimates of how that alters the spin kick, the kick of the protoneutron star. That's something I hope we can advance further as we are able to use codes like Phoebus to evolve the shock even further out than what other groups have been able to do so far. But I do think there will be an impact.